Okay, thanks, Bob. Thanks. Yeah, it's great to be here. Thanks so much. Yeah, so I'm going to be telling you about the MOSFIRE Deep Evolution Field Survey, otherwise known as MOSDEF. Really what I want to talk about is how we can gain insights into the physical properties of galaxies at high redshift. And it's really fun to come to Riverside because it's a little bit like bringing coals to Riverside or Newcastle, because there's so many people in this project who work here at Riverside. In addition to my co-PIs, Brian Sayana, Baro Mobasher, and Naveen Reddy, you can also notice the names of some of the wonderful grad students here at UC Riverside. And I'm today going to talk a bit about some of the work that we're doing at UCLA, and in which my graduate student Ryan Sanders has taken an important role. So anyway, so what we're going to learn about today is the properties of high redshift galaxies. So just to get started, because I know we have a mixed audience, we want to talk a little bit about galaxies today. So a galaxy is a collection of gravitationally bound stars, typically billions of stars. You know, we live in the Milky Way galaxy. That's an example of what we call a spiral galaxy. So here we have spiral galaxies on the left, and we have what we call elliptical galaxies on the right. These are galaxies in the universe today. And you can see that not only are the spirals and ellipticals sort of typically different shapes, but they also have different colors, and it turns out they probably formed in slightly different ways. And so understanding where the origin of the vast variety of galaxy types and luminosities and colors and sizes and masses, understanding where this vast variety comes from is one of the key goals for modern astronomy. And so we can try to understand, the formation of galaxies using what we call the lambda CDM cold dark matter framework. Okay, and so according to this framework, the matter in the universe is mainly composed of dark matter. So 85% of the matter in the universe is dark matter, not the baryonic matter that we're familiar with. And the idea here is that galaxies form and grow where the dark matter distribution is the densest and becomes denser as time goes forward. And so as of now, astronomers and physicists have a well-described evolution of the distribution of dark matter in the universe through merging and accretion events under the influence of gravity alone. And what I'm showing here is actually, this is a snapshot from a project called the Millennium Simulation. This is actually run about 10 years ago, a little bit longer than that ago. And what you see is a computer model of the large-scale structure of galaxies in the universe, except this is actually only showing the large-scale distribution of dark matter, okay? And so while the evolution of this distribution of dark matter is very well understood, apparently, at least on the largest scales, if we want to make a realistic galaxy, we have to include a model that takes into account not only processes related to dark matter and gravity, and the underlying cosmological model, but we also need to take into account lots of processes that involve the baryons, the atoms, and also the photons, okay, and describe the process in which stars are formed and die, and the energetics associated with this, and the way that chemical elements are deposited into the interstellar medium and beyond galaxies, okay? So capturing all of these processes is very complicated, and you can see here, this is a computer simulation of a galaxy forming about 10 billion years ago. It's a galaxy that's probably going to grow into something that looks like a pretty massive galaxy by today. And this box in the simulation is around 3 million light years on a side. Okay, and you can see this is the sort of central region where the mass density is highest and matter is streaming in, okay, to the galaxy. It's accreting onto the galaxy, and the color coding here is telling you about the temperature of the gas, and the intensity is telling you about the density. But models of this type that actually try to capture all the processes related to gas and star formation and what we call feedback, where the energy from the stars and their deaths actually affects the star formation process itself, these are very hard to do and very hard to describe accurately. So the question is, how do we try to address this problem of making realistic models of galaxy formation? And so what we're going to talk about today is one way of approaching this problem. And so we're making use of the finite speed of light, according to which distant objects in distant parts of the universe are observed at earlier times, and using telescopes effectively as time machines. And so the idea, what I want to talk about today, is how we might construct the timeline of galaxy formation directly with observations of galaxies at earlier epochs. So distant galaxies where we're looking back in time. And this is just an example of various different telescopes. Mainly today, we'll talk about observations with the Keck telescopes. Okay. You can see, for example, here are some images of galaxies taken with the Hubble Space Telescope. So these are images of galaxies as they existed maybe 10 billion years ago. And you can see that these images look a little bit different from the images I showed you at the beginning. So those initial images of spiral and elliptical galaxies, so these are taken from the Sloan Digital Sky Survey, which is a survey of the quarter of the whole sky, but mainly focuses on the universe today, whereas these images of galaxies, they look more lumpy and irregular, and that's fairly typical for galaxies that are actively forming stars in the early universe. Okay, so if we actually try to construct the story of galaxy formation, there are a bunch of key questions that we'd like to try to answer in this, in this story. Okay, and so one of the things we want to understand is what the physical processes are that drive the formation of stars in individual galaxies. So this is a plot that lots of astronomers like to show. If you go to some meetings, you'll see this plot, I don't know, maybe 25 times throughout the course of the week of a conference. But what we're looking at here is a plot of, so basically, as a function of time. So here we're going back in time, and then time moves forward from right to left. This is a plot of the rate at which stars are being formed in the universe per unit volume. Okay, so you can see that at early times, the star formation rate was lower, and then over the next few billion years, the star formation rate density in the universe reached some peak level, and then over the next several billion years, it declined by about a factor of 10. And so you can see the universe today is actually quite boring compared to how it was 10 billion years ago when the activity level was much higher. Now, this plot is actually showing some kind of globally average rate of star formation in the universe as a function of time. But one of the things we want to understand is how the individual star formation histories of galaxies contribute to this global history, and also what drives those processes in individual galaxies. Something else that's related is we want to understand how matter is assembled in galaxies. Okay, so that snapshot from this computer model that I showed you a minute ago, was showing matter accreting onto galaxies in what we would call smooth accretion. Okay? Another way that a galaxy can grow is by colliding with another galaxy in what we call a major merger. And that's what's shown in these images here, images of colliding galaxies. Okay? So one of the things that we want to understand is what is the relative importance of these processes of growth, basically matter coming in smoothly in very small lumps or streams as opposed to large collisions. Because presumably the way that the galaxies look today shows some reflection of the relative importance of these processes. Another important question, sorry, this image is getting a lot of mileage, I should probably update it, it's so old. But another important question is, how do galaxies exchange gas and heavy elements with the intergalactic medium, so the material in between galaxies? This process here, this process of inflow of material onto galaxies is sort of a generic property of simulations of galaxy formation. It turns out it's pretty difficult for astronomers to observe this directly. One of the things we do observe quite commonly, especially in the early universe when galaxies are very intensely forming stars, is that gas gets driven out of galaxies at rates of up to hundreds of kilometers per second. Okay, this is a nearby starburst called M82. This is another plot that's very popular among astronomers to show sort of emblematic of the process of outflows. Yeah, so the main thing to keep in mind is that galaxies are not closed boxes, but they're exchanging mass and momentum and energy with their surrounding environments. And this is just showing an example of the material being launched out of a galaxy and basically being driven by the input of momentum and energy from the star formation process. Okay, and then the last sort of key question that I want to highlight, I'm not going to be talking too much about this, but this is something else that a lot of astronomers worry about, is what the nature of the coevolution is between black holes and the galaxies that host them, the stellar populations that host them. So this is sort of a cartoony plot. There actually corresponds to plots of real data that astronomers have, but I think it illustrates the point here. The majority of galaxies in the universe today host supermassive black holes at their centers. And one of the things that's remarkable, beyond just that fact, is is that the mass of the black hole at the center of galaxies is very strongly correlated with the mass of the bulge components of the galaxies, or in elliptical galaxies, just the mass of the whole galaxy. Okay, so you can see that there's a very tight correlation between these two masses. And the question is, why is this so? Okay, the gravitational sphere of influence for these black holes will be basically 3 orders of magnitude smaller than the scale of the whole galaxy itself. So the question is, why do these masses seem to know so much about each other? Okay, and so the question is, is there some kind of feedback between the formation of the black hole and the formation of the galaxy itself? And this is something that's a very active area of research. Okay. All right. So, so today we're going to be talking about going back in time. Okay, about 10 billion years ago. To astronomers talk about using redshift. So basically that's an empirical quantity, but if we measure it for a galaxy, it basically tells us how far back we're looking back in time. Okay, so we're going to be looking at galaxies mainly at redshifts 2 to 3, and that in terms of time frame, that's looking back about 10 billion years in time. And as I already mentioned, sort of looking back that far in time, okay, takes us to an epoch that hosts both the peak of the rate at which stars were forming in the universe, and also the rate at which black holes were growing. Okay, as I said today, the majority of galaxies host these supermassive black holes at their center, but if you actually want to know when a lot of the growth rate of these black holes was at the peak level, we have to go back in time. So this, again, this is this plot of the rate at which the stars are being formed in the universe as a function of time. And this plot on the bottom, this basically tells us sort of the rate at which black holes are growing as a function of time. Again, on the right is further back in time. As we move to the left to a redshift of 0, we're going to the current epoch. Okay, you can see there's this peak level of activity several billion years back in the past. And so if we go back to this earlier time, okay, this time of this epoch of redshift 2 to 3, we see some qualitative imprints of the local galaxy population. So we see that there are red galaxies and blue galaxies, just like there are in the early universe. And we see that to some extent, the red galaxies like to live in denser environments than the blue galaxies. But there are also some very important qualitative differences. And so the early galaxy population is not just sort of a smoothly evolved back version of the current galaxy population. So some of the key differences are that galaxies of a fixed mass, so let's say 10 billion times the mass of the sun, they're smaller and they're much more actively forming stars. They contain much more gas in their interstellar media compared to the amount of stars that they have. If you look at disk galaxies, we do find galaxies in this early epoch of the universe that are rotating. Our Milky Way galaxy rotates. But the difference between disk galaxies in the early universe and disk galaxies today is that these early disks are much more turbulent. Okay? So our Milky Way spins, basically the rate at which it spins is 2 orders of, or almost between 1 and 2 orders of magnitude faster than the random motions in the interstellar medium. And in the early universe, basically, these rotational and random motions are comparable. We also find differences in terms of the level of star formation activity on a galaxy-by-galaxy basis. In the local universe today, the most massive galaxies are predominantly red. We call them red and dead. Okay, they're not making new stars. But if you go back to these early times, even the massive galaxies are still actively forming their stellar populations. And another thing, so remember I showed you that image of that starburst M82 with the large-scale outflow of gas. If we look back to these earlier times, large-scale outflows are fairly ubiquitous. Okay? In most star-forming galaxies that we've observed so far, we see these big outflows. Okay? And by the way, I should say, because I know this is an audience that has diverse interests, if you have questions at any time, if you think I've used something that doesn't, some jargon word that doesn't mean anything to you, please break in and interrupt. And if you have questions, interrupt. Okay? I far prefer that than the alternative. Yeah.
You asked for it.
Okay, go for it. I didn't think you'd have a question. That was like for the grad students. Okay, go for it. Yeah, go for it.
Maybe it's something I don't understand. Galaxies of fixed mass are smaller, more actively star forming, and more gas rich. What do you mean? Galaxies of fixed mass.
So I mean,
What are you comparing to? What do you mean?
I mean fixed mass in stars. Fixed mass in stars.
Fixed stellar mass.
Fixed stellar mass. Yeah. Like if you look at the mass-size relation, right, at redshift 2.
As compared to what?
Redshift 0. So like fixed stellar, as I'm saying, if you take a redshift 0 galaxy today, that has 10 billion times the mass of the sun, and then you take one at redshift 2 that has 10 billion times the mass of the sun and stars, their structures are going to look different.
Oh, right. So you're comparing at different times.
Different times.
Right.
Yeah, so I'm saying the redshift 2 galaxies of the same mass as the redshift 0 galaxies are smaller and more gas rich. Sorry, I should have made that more clear. Yeah. Okay, other questions? Any other question? Okay. All right. So let me just put up these big questions again. Okay. So some of the things that we're trying to understand are, how are stellar mass and structure assembled in galaxies? What are the physical processes that drive star formation in individual galaxies? How do galaxies exchange gas and heavy elements with the intergalactic medium? And what is the nature of this coevolution between black holes and stellar populations? And so hopefully I've tried to motivate a little bit why we're going back in time so far. It's this active period of the universe when the patterns that we see in the universe today are not all set. And what we're going to talk about now is why using rest frame optical spectroscopy, which is what we're using the MOSFIRE instrument on the Keck telescope to do, why rest frame optical spectroscopy is a very powerful tool for trying to address these questions. Okay? Yeah?
Is there a similar figure for a galaxy formation versus Z?
A galaxy formation versus well, that's sort of you mean like when a galaxy forms? I mean, so the thing is that galaxies are sort of like continuously growing. So I don't know that you can, so it's difficult to say like when exactly a galaxy forms. It's sort of like, it's not like a discrete event in time. So we can make a plot of like how the mass of a galaxy grows with time, but it'll be sort of like a continuous, we could, if you want to say like the time at which the galaxy reached like half its mass. But I'm not sure that it's not a trivial thing to do actually to try to reconstruct. Yeah, sorry.
Related to Bob's question, presumably the statistics of a given size are vary wildly across. I'm guessing, I have no idea, between what I know at redshift 0 and redshift 2. I mean, if I take 10 billion star galaxy of redshift 0 and compare it to something at redshift 2, and you said, the dynamics is very different, or things like that. But what's the statistic? Presumably you have a lot more stars you can study now than then, or is that?
So the Sloan digital skies, you're talking about the samples, like how many galaxies can we study? So, I mean, locally, like we have samples of like maybe like 1 million galaxies. But I think for the high redshift studies, in terms of like mass and size plots, I mean, we have access to maybe tens of thousands of galaxies.
So is it, you're saying
so it's enough. I mean, that we're not limited by, I don't think we're limited by the
so
number.
statements are very general, interesting, that if I always, to a large extent, it's always true.
I don't think it's a controversial statement, that if you look at something of a fixed mass, it'll be smaller in the past. Okay, so now the question is, what do I mean by rest frame optical spectroscopy? What are the tools that we're going to be employing to study these galaxies? Well, so I'm showing you on the top a spectrum of this is a nearby galaxy that's strongly forming stars. And you can see there are several strong emission lines here, okay? And we're going from 4,000 up to 7,000 angstroms. If you like nanometers, this is like the visible part of the spectrum, 400 to 700 nanometers. And you can see there are several strong emission lines. This come from singly ionized oxygen. This is ionized hydrogen, doubly ionized oxygen, more hydrogen. This is a nitrogen line and some sulfur lines. So this is sort of the suite of emission lines that we're going to be studying in the early universe. And on the bottom, you can see examples of what we call absorption line spectra. So these are the spectra of galaxies where we can really take a look at the types of stars that are in the galaxies. This would be a slightly younger galaxy, and this would be a slightly older galaxy. Here we're looking more just in the blue part of the spectrum. But you can see there are some strong lines here from calcium. There's some stuff from magnesium that's outside of the range of the spectrum. Here, right around 4,000 angstroms, you can see there's a drop-off in the spectrum, and the strength of this break here is another probe of the mixture of stars in the galaxies. Okay, so the thing is that at a redshift of greater than 1.4, which is basically all the stuff that I'm going to be talking about today, the bluest of these features, this oxygen 2 line here, okay, moves past 9,000 angstroms. So studying these lines becomes a near-infrared problem. Okay, we need to use near-infrared spectroscopy to try to address the properties of these lines that are emitted as optical photons. Okay, and so we were thinking about how to do this several years ago. But in order to assemble statistical samples of these rest frame optical measurements, we really needed a transformative boost in both signal-to-noise and survey efficiencies for near-infrared spectrographs on large ground-based telescopes. Okay, and so that's that's what I want to talk about. Is basically the study of these features that form the basis of sort of traditional optical spectroscopy in the local universe and how we apply them to the early universe. Okay. So I want to tell you about our project where we tried to do this. This is the MOSDEF survey. And I want to tell you about what we've been learning about the physical properties of high redshift galaxies. And then I want to just finish up with a couple of things that we're thinking about studying in the future. Okay. So as we were thinking about how to try to survey the distant universe, that epoch of peak star formation and black hole accretion density in the universe, we're thinking about what the sort of key requirements would be for designing a project to study the distant galaxies. And so specifically, we wanted to look at this redshift range of around 1.5 to 3.5. So this corresponds to look-back times of about 9 to 11 billion years. And so we wanted to obtain rest frame optical spectroscopy covering all of the strongest rest frame optical emission lines that I just showed you a plot of. This is between 3,700 and 7,000 angstroms. We felt it was necessary to assemble a large sample of objects. So large by high redshift standards, early universe standards is only about 1,000 compared to the existing work at the time. And so we also wanted to look at galaxies that had a wide range of properties. So not just strongly star-forming galaxies, not just dead galaxies, but a really wide range of stellar populations. And then furthermore, we wanted to look at evolution as a function of time. So basically look in multiple bins of redshift so we get different snapshots of the universe at different cosmic epochs, okay? And so our project, the MOSFIRE Deep Evolution Field Survey, MOSDEF, achieves these goals. That's how we designed the project. And so this is a picture actually taken here in the physics, outside the physics building. I didn't like this picture because I was sort of like put off in the corner and hunching and stuff. But you can see this was actually taken a couple of years ago, and you can see many familiar faces in the picture. So this is our team consists of 6 co-PIs, all within the UC system, and then many amazing graduate students, a few of whom are right here and even sitting in this room. So Bill and Irene and Tara have all made wonderful contributions, and Laura before she graduated as well. So, okay. So the key, sort of the star of the show for our project is this amazing instrument that was commissioned on the Keck telescope in the spring of 2012. This is MOSFIRE. Okay, so this is the multi-object spectrometer for infrared exploration. The co-PIs of this instrument are Ian McLean at UCLA and Chuck Steidel at Caltech. And so MOSFIRE enables near-infrared spectroscopy, so that's spectroscopy between 0.9 and 2.5 microns over a field of view that's 6.1 by 3 arc minutes. So remember, the full moon is 30 arc minutes in diameter. You have to do one near-infrared filter at a time, but one of the interesting or sort of novel properties of MOSFIRE is that you can observe up to 46 objects at once using this thing called the cryogenic configurable slit unit. And this is an example of what we call a slit mask of data from MOSFIRE. You can see all the, so does anyone know what kind of spectra we're looking at here? What wonderful astrophysical object are we studying? No, what are you raising your hand for? Cheater. Anyway, okay, yeah. Anyone know what this is a spectrum of? Close. It's the sky. It's the sky. Yeah, close. What? It's an emission spectrum. Yeah. Right. Yeah, these are emission lines that come from molecules in our atmosphere. Okay, and they're the bane of our existence. Yeah, okay, so MOSFIRE enables measurements of rest frame optical spectra. So these are photons that are emitted as optical photons, but by the time they get to us, due to the expansion of the universe, we observe them as infrared photons. Okay, oh yeah.
This is basically your background.
What, this is our background. This is our background. Yeah, and it's a lot brighter than our signal.
No, it's your foreground, but it's the background.
Yeah, so probably the most important step in our data reduction is subtracting this off. And so, right, so there are a couple of key features of MOSFIRE that are worth pointing out. So one is that even just for studying single objects, the detector improved so much that there's a sensitivity boost of at least a factor of 5 relative to the previous generation of near-infrared spectrographs at Keck, like NIRSPEC was the long-slit spectrograph that was the predecessor. So this leads to emission line sensitivities of a few times 10 to the minus 18 ergs per second per centimeter squared in 2 hours. If that number means nothing to you, what it corresponds to in practice is that we can look at stars forming at a rate of around 1 solar mass per year at a redshift of 2. So while in principle you can observe up to 46 galaxies simultaneously, in practice, just due to the way you make masks, and I should say Brian Sienna designed our masks. He did an amazing job. In practice, you can get around 30 objects at once, okay? But if you think about what these two things, the sensitivity boost and the multiplex factor mean, so a factor of 5 times a factor of 30, what this means is that you have an increase in survey efficiency of more than 2 orders of magnitude with MOSFIRE compared to the previous generation of instruments. Okay, so I want to say a little bit about how our project was designed. So we were awarded what's called a large or LMAP program from the University of California Time Allocation Committee, which meant that they gave us almost 50 nights of Keck time using the MOSFIRE instrument between 2012 and 2016. Where did we point the telescope? Well, we looked in these places called the legacy fields. And these are little patches of the sky that extragalactic observers have agreed to point lots of different telescopes at, so that you get information over many different wavelength ranges for the same galaxies. And we looked at, as I said, we want to do an evolutionary study. So we looked in a few different redshift ranges between about redshift 1.4 and 1.7, 2.1 and 2.6, and around 2.95 to 3.8. Again, this is 9 to 12 billion years ago. I'll talk in a second about why we chose these particular ranges in redshift or look back time. And we assembled about 1,500 galaxies and measured 1,300 redshifts, which means 1,300 galaxies from which we can do science. And the other thing about our project was that we identified galaxies for spectroscopy in the H band, which is observed 1.65 microns, okay? Which corresponds to looking in the rest frame optical, which is very similar to what astronomers do in the nearby universe. So in many ways, it's analogous to when people do a survey of the local universe, okay? All right, these are some maps of where we pointed the telescope in these 3 different sort of key target fields. We have the Cosmos field, this is the Goods North field, this is the Aegis field. These are these places in the sky that have lots of ancillary data. So the Hubble Space Telescope, the Spitzer Space Telescope, the Chandra X-ray Telescope, Herschel Infrared, VLA Radio Telescope. There's lots of ground-based imaging spanning, the optical and near-infrared. So with all of these other data sets, we learn about the detailed morphologies of the galaxies, from the Hubble Space Telescope. We learn about the stellar masses and other aspects of the stellar populations. We can figure out which objects are active galactic nuclei, actively accreting black holes by looking at the X-ray and near-infrared and infrared wavelengths. There's existing spectroscopy from various surveys. And the other thing that was actually really important was that other teams had already made extensive catalogs of all the galaxies in these fields just based on their imaging and prior spectroscopy. And so it really allowed us to very effectively target the MOSFIRE spectrograph, like figure out which targets to put on each one of those masks, so that each time we got a sample of 30 galaxies, we were really getting the galaxies we wanted and not galaxies at different distances or properties that we didn't want to study, okay? All right. So I wanted to say why we were looking in those particular redshift ranges, and it has to do with our atmosphere and the fact that we haven't yet gone into space with the James Webb Space Telescope. So remember, we were looking at these redshift ranges 1.4 to 1.7, 2.1 to 2.6, 2.95 to 3.8, okay? And so we selected these ranges to optimize the detection of these rest frame optical emission lines in windows of atmospheric transmission, okay, which correspond to actually the filters that astronomers use in the near-infrared part of the spectrum. So you can see there are these filters, the K-band filter, the H-band filter, the J-band filter, and then this Y-band filter. You see the wavelengths where these filters fall, okay? And so, for example, this is our real sweet spot right around redshift 2, okay? You can see that those strong emission lines that I showed you before, the oxygen 2 line, the H-beta and oxygen 3 lines, the H-alpha, nitrogen 2, and sulfur 2, all these lines fall within windows of atmospheric transmission, okay? At higher redshift, at redshift 3, the key lines fall in the H-band and the K-band. You can see the wavelengths where these are 1.6 and 2.15 microns. And then at lower redshift, we have our key lines in the Y band around 1 micron, the J band around 1.25 microns, and the H band around 1.65 microns. Okay? So that's why we chose those redshift ranges, because these are the ranges where we can actually obtain the spectral features that give us the insights into what's going on in the galaxies. Okay, so I just want to say a little bit about the statistics of the project. Okay, so we observed 54 slit masks, so that corresponded to around 1,500 targets and about 150 galaxies that we didn't plan to target but happened to fall in our slits. And you can see this is a histogram of all the redshifts that we measured. We did some detailed statistics of our success rate and the types of things that we were studying based on our early data from the first couple years. So only a minority of targets that we studied actually had previous spectroscopic redshifts. That's good because it means that we were not biased to only look at the types of galaxies that would have previously measured redshifts. We had a very high overall success rate. So basically 80% of anything that we targeted, we actually confirmed. So that was really good. About 10% of our sample are AGNs of some type. That's actually overrepresentation relative to the sort of cosmic rate of these actively accreting black holes. And we looked at galaxies over a range of around 1 billion up to 300, a billion up to about 300 billion times the mass of the sun. So we're not looking at like tiny little galaxies. We're kind of looking at fairly hefty galaxies in the early universe. And they're forming stars at a range of around 1 to 1,000 times the mass of the sun per year. Typical star formation rates in our sample were around 20 solar masses per year. Okay, and here's some of the data from our project. So you can see what I'm showing you here in each one of these panels. I'm sorry, I don't know like which one to look at. Maybe I'll look at this one for a change. For each galaxy here, these are examples of galaxies at redshift 2. So we're going to look back time around 10 billion years. Okay. So the bottom panel here shows the broadband, what we call spectral energy distribution, going from the observed optical through observed mid-infrared. Okay. And then the top shows the spectrum that we obtained from MOSFIRE in the J band, the H band, and the K band. And these are ordered basically in terms of decreasing ratios of UV to optical or UV to infrared light. Okay? And what that means is that the galaxies up here are like the youngest, the most actively forming stars relative to their accumulated stellar mass. And over here, we get more massive, sort of more passive galaxies. And this one here, actually, I don't know if you can tell, if there's time at the end, I'm going to show you this. We actually see some absorption lines as well, not just emission lines. Okay. All right. So I'm going to talk a lot about what we can learn from these emission lines. And so I want to talk about what it is that we're actually sampling when we obtain a spectrum of a redshift 2 galaxy with MOSFIRE. Okay. So in the nearby universe, if we were to look at a close-by galaxy, this is a galaxy called M83, and we were to zoom in on one of its star-forming regions, this is I can't remember what the name of this one is. Sorry, I don't remember. Anyway, but this is what we call an H2 region or a star-forming region. And the emission lines that come from this star-forming region, are a very powerful probe of the H2 regions, the star-forming regions. And we learn about the stars in these H2 regions. We learn about the chemical content of the gas. We learn all sorts of the dust content, all sorts of interesting stuff. And so locally, when people look at a spiral galaxy, for example, they can put slits on individual H2 regions. For example, the Chaos project is a great study of nearby H2 regions, and they can get a resolution, like a spatial resolution of something like 35 parsecs, okay, which is much finer than the detail that we can study in these distant galaxies. So if we step out a little bit, if we think even in the local universe, about the Sloan Digital Sky Survey, from which I've already shown you a couple of examples. So Sloan, rather than using slits like we do with MOSFIRE, Sloan actually points a fiber at a galaxy, and all the light goes into this fiber, and you get a spectrum from the fiber. So the fibers are around 3 arc seconds in diameter for Sloan, which corresponds to a scale of 6 kiloparsecs at the typical redshifts at which these galaxies are studied in the Sloan Digital Sky Survey. Okay, so we're looking at regions now 6 kiloparsecs in diameter. Now in MOSDEF, our slits are 0.7 arc seconds, and this probes a region of around 5 kiloparsecs across. So here are some examples of MOSDEF galaxies that we've probed, and these are the slits, and you can see here the galaxies they fit into. But we're looking at regions about 5 kiloparsecs across. So it's very different from the 35 parsec resolution of these nearby surveys like the Chaos project. Okay, so what is it we're actually collecting when we get the light from this galaxy in one of our MOSFIRE slits. So for a spatially unresolved source, we're basically treating the galaxy as a point source. Most of the things we're studying, we're treating that way. The emission that actually goes in our slit, it's a galaxy integrated quantity, which means it's sort of weighted by the surface brightness of the different parts of the galaxy. And it's an ensemble average of all these star-forming regions and the diffuse gas in the galaxy. Okay, so I'm going to come back to that at the end of the talk. So with that in mind, I guess as a sort of caveat about how we're kind of adding together all these different parts of the galaxy when we obtain one of our spectra, let's think about the types of things that we try to measure from these spectra. So one of the things that you can do when you have a spectrum, okay, is you can look at the amount of dust extinction that occurs, that's sort of affecting the gas and stars in these star-forming regions, okay? And you can do that by looking at the ratio of this H alpha to H beta emission. Okay, that tells you about how dusty the star-forming regions are. If you know the amount of dust extinction, you can take the luminosity of this line here. Okay, so this is the third to the second energy level of hydrogen, right? And the luminosity of this line, once you correct it for dust, tells you about the rate at which stars are being formed. If you look at the pattern of several emission lines from oxygen and hydrogen, oxygen, hydrogen, nitrogen, sulfur, the pattern of these lines is actually sensitive to the overall chemical content of these star-forming regions, the metallicity. If you look at a couple of other features, so this is actually a pair of emission lines, as is this one. These are what we call doublets, okay? So the shapes of these lines, the relative strengths of the two doublet members, tells you about the density of gas in star-forming regions, the physical density of particles per cubic meter, okay? There's another parameter called the ionization parameter. This is a little bit difficult to describe, but it basically tells you about the overall level of ionization in these star-forming regions. And this ionization parameter determines the appearance of the spectrum in terms of the strength of emission lines of different ionization states of the same element. And it's defined in terms of the density of ionizing photons to particles in star-forming regions. And it's something else that we can probe, okay? We can also look for evidence of AGN activity, so basically that the spectrum of the accretion disk around a black hole is illuminating gas in the interstellar medium in these galaxies because it looks different from the spectrum of massive stars, and we can do that by looking at these emission lines, their pattern. Now, in addition to looking at the strengths of these lines, we can also look at their shapes. Okay, turns out the widths of these lines tell us something about kinematics, motions in the galaxies, and we can combine them with the sizes of the galaxies and the virial theorem to estimate the dynamical masses of these galaxies. But we can also look at the detailed shapes of these lines and look for deviations from a simple Gaussian profile and underlying broad components that might tell us either about AGN activity or else about large-scale outflows from the galaxies, kind of akin to the scenario that we saw with that nearby starburst galaxy, M82. Okay, so these are the types of things that we can learn from the spectra that we're collecting with MOSFIRE. Yeah?
What is the mechanism for these big outflows?
Yeah, sure. Well, it's debated exactly what the dominant mechanism is, but the idea, there are a few things. So one is if you have a very high surface density of stars going off, and there are a lot of young massive stars that will die and explode in supernovae, the idea is that there's energy associated with the hot gas from the supernova that will sort of push out the interstellar medium in the direction of sort of like the steepest pressure gradient, but also that there's momentum from the radiation associated with massive stars and momentum associated with the supernova itself that will also sort of act to push the gas out. And also that radiation will push on dust grains in the interstellar medium that will also tend to loft the gas out of the galaxies. So there are many different processes, but it's associated with the star formation process, either from the radiation from massive stars or associated with the supernova explosions. Now, it's also thought that the energy input from accretion onto the black hole can also contribute to outflows when you have an actively accreting black hole. Okay. But this is actually very important because if you don't have a good description of this feedback process, if you have a model for galaxy formation that doesn't try to do a realistic job of describing feedback in these outflows, you make galaxies that don't look like galaxies today. You make too many big blue things. And so the galaxy population in the absence of feedback just doesn't look like the real one. Okay. So, so we've been doing lots of stuff with our wonderful data set of spectra, and we're considering many different science questions. And so we've written down some of the ideas that we're thinking about in a paper by Mariska Creek from a couple years ago. So we're looking at star formation and the growth of galaxies, dust attenuation, metallicities and physical conditions like the density of gas and the excitation in the star-forming regions. We're looking at how gas cycles in and out of galaxies and outflows and inflows. We're looking at the dynamical masses of galaxies and how their structures evolve. We're looking also at the growth of black holes and how black holes and galaxies co-evolve. And we're even looking at the abundance patterns in stars and how galaxies are assembled. And so this is just a list of some of the papers that have come out or are about to come out, and you should recognize the names of some of your friends here. What I want to spend the rest of the talk focusing on in the remaining time is this question of metallicities and physical conditions in star-forming regions, because this is what we've been thinking a lot about at UCLA. Okay, so first of all, what do I mean by metallicity? So in the context of today's talk, I'm talking about the gas phase oxygen abundance. In general, when people say metallicity, they mean the abundance of heavy elements, so everything heavier than helium relative to hydrogen. And so this is sort of a cartoony diagram of an interstellar enrichment cycle, or the chemical enrichment cycle in our Milky Way. You know, the idea is that you have atomic gas that cools to the molecular form out of which you make new stars. Stars fuse heavier elements in their interiors, then they explode and return these heavy elements to the interstellar medium. Here's a supernova remnant, and then basically new stars form out of gas that has been enriched by the previous generations of stars, okay? But in addition to this process of stars enriching the interstellar medium, okay, we also need to think about the importance of gas that comes in. We also have to think about the importance of gas that goes out, okay? But all of these processes, star formation, inflow, and outflow, will affect the metal content of a galaxy. And astronomers have actually tried to get more insight into these processes of gas flow by looking at how the metallicity, so the gas phase oxygen abundance, which you'll see this a few times going forward, we write it as 12 plus log O over H, but that's basically just another word for metallicity or oxygen abundance. But you can see that in the local universe, so this was done with the Sloan Digital Sky Survey, about 50,000 galaxies from the Sloan Digital Sky Survey, there's a relationship between how much metals, the proportion of metals in the interstellar medium, how that is related to the stellar mass of a galaxy, such that more massive galaxies have a higher oxygen abundance in their interstellar medium. Okay, but looking in detail about this relationship, it may actually tell us something very fundamental about how gas cycles in and out of galaxies. Okay, it may tell us about the importance of these outflows as a function of galaxy mass. And so the question is, if we want to look at this relationship, but we don't only want to measure it at redshift 0 today, but we want to look at how this evolves over cosmic time, which is what we do want to do, because I think this is going to provide vital constraints on this process of feedback. We really need to think hard about how we estimate the metal content in galaxies, not just today at redshift 0, but also in the distant universe. Okay? So if we lived in a perfect universe, well, many other things would be true. But one of the things is that we would be able to measure the oxygen abundance of every galaxy using what we call the direct method, okay? And so this shows an example of a spectrum where you see some of those lines that I've shown you before, but you also see this weak line from oxygen 3 at a wavelength of 4363 angstroms, and measuring the strength of this line relative to this line, okay, you can see these are from the same ionization state, okay, but they're actually probing different energy levels. The 4363 level is coming from here down to here. The 5007 line comes from the intermediate down to one of the ground states. The relative strength of these lines tells you about the temperature of the gas in the star-forming regions. And if you have that, and then you also have the strengths of these strong lines, you can actually, based on atomic physics, figure out how much doubly ionized oxygen there is. And there's an analogous feature to this one that you can use for singly ionized oxygen. Basically, all the oxygen is either doubly ionized, singly ionized, or neutral. And so you can actually estimate how much oxygen there is, like for real. And this would be an equation that you use to do it. And you can see here T, this is this temperature that you get from the ratio of these two lines. okay? And this is what we call the direct method, based on, as I said, physics, okay? And this would be great if we could do this for all galaxies, but unfortunately we can't, okay? This line is very weak, and in most of the galaxies that we study, we just don't detect it, so we can't do it this way. So rather than using physics to estimate oxygen abundance, we use astronomy, and that means, basically taking the, in the local universe, taking cases where we could get direct oxygen abundance measurements, okay, and then measuring how this real oxygen abundance estimate compares with an empirical indicator that we can measure, which is just the ratio of these different strong emission lines that are easy to detect over a wide range of redshifts. Okay, so these direct metallices are typically too hard to measure at early times, so we commonly estimate the oxygen abundance from calibrated ratios of lines that we can measure. Okay, so you measure this relationship between the line ratio that you can measure and the direct metallicity. That's one way. Turns out you can also use what we call photoionization models. I would not advocate doing that. And there's some common patterns of strong emission lines. This is the ratio of nitrogen 2 to H alpha. We can use more line ratios. This is O3N2. This one's N2, O3N2, O3 to H beta divided by N2 to H alpha. You can use another ratio called R23. But the fact is that the fact is that these have all been calibrated in the local universe. Okay. And so this is just showing you visually, right? So here, this would be this N2 to H alpha. Here's the N2 to H alpha divided by, or O3 to H beta divided by N2 to H alpha. This is that R23 one, O2 plus O3 divided by H beta. And you can see these lines are detected in our MOSFIRE spectra, right? So in principle, we can do this with MOSFIRE for our redshift 2 galaxies. Okay, but here's the question, right? So people measure these lines in nearby H2 regions, nearby star-forming regions, and they can tie the direct oxygen abundances in these H2 regions to the patterns of strong lines they observe. So the question, though, is that when we go and we look at our redshift 2 galaxies, are they actually analogous to the individual H2 regions for which these abundance indicators of oxygen have been calibrated, okay? And we actually have grave concerns about this, okay? Because if you look here, okay, so there are various ways in which we can try to answer that question about whether the high redshift galaxies are actually analogous or not. In the nearby universe, this is another plot taken from the Sloan Digital Sky Survey, and this is not my plot, this is from Kaufman et al. 2003. You can see a plot of that O3 to H beta versus N2 to H alpha. This is a very well-defined locus of star-forming galaxies. These are lower metallicity galaxies, and these are higher metallicity galaxies. They're not randomly distributed in this space. They're very well behaved. And here are active galaxies. These are active galactic nuclei of various different kinds. Okay, now, so you can separate between the star-forming galaxies and the AGNs. Now, the thing is that based on small initial samples of high redshift galaxies where we tried to put them in this plot, it was very hard before MOSFIRE, we had a hint that maybe there was something different about these high redshift galaxies, okay? And then when we conducted MOSDEF and other people used MOSFIRE in this project called the Keck Baryonic Structure Survey, we found that a larger sample of redshift 2 galaxies, as indicated by these green points, confirmed our earlier suspicions, that the high redshift galaxies, these green points, do not lie right on top of the redshift 0 star-forming galaxies, okay? And so the question is, what's going on, okay? Why do these high redshift galaxies look different? And so there are various reasons why the distribution of high redshift galaxies in this space of emission line ratios could look different. You know, and these are the various things that we're trying to understand, okay? So in these star-forming regions, if, for example, the spectrum that's illuminating the gas in the star-forming regions is harder, okay, has more high-energy photons relative to low-energy photons, that might be one way that the points would be offset this way. If the intensity of ionizing radiation relative to particles was higher, that would also affect where the points are. If there was a different abundance pattern of nitrogen and oxygen, that would also displace points in a certain direction. Turns out that the physical density in these star-forming regions was different. That could also displace points in certain ways. So we have many different factors that might be different in these high redshift star-forming regions. And they're interesting in their own right because they'll affect the way in which stars form. But they're also interesting because if we can understand what's going on, then maybe we can understand how to estimate oxygen abundances in these distant galaxies. And so that's what we've been trying to do a bit. So one of the things that we can measure in our spectra is we can actually look at that physical density of star-forming regions in these distant galaxies. And we do that by looking at the relative strengths of the doublet members in the oxygen-2 and sulfur-2 doublets. And these are some examples of our oxygen-2 doublets and our sulfur-2 doublets. So these are measured in the J band. These are measured in the K band, okay? And you can use the relative strengths of these lines to infer the electron density in these star-forming regions. And we did this for about 70 galaxies. And we can estimate the electron densities here, and we can compare them with the electron densities measured at Z of 0, okay? And what you can see, okay, is that in the redshift 0 sample, this is from Sloan, based on the doublet ratios of sulfur-2, that the typical physical densities are around 25 particles per cubic centimeter, whereas at redshift 2, we find a density that's an order of magnitude higher. Okay? So that's really interesting. The gas out of which these stars are forming is 10 times denser in these earlier galaxies than the galaxies today. I mean, I told you something earlier. I said that galaxies of fixed mass are smaller. So the question is it just a geometry effect, or is it something that's more local, like microphysics? But that's a really interesting thing that we uncovered. Turns out, though, that the fact that these star-forming regions are denser, that doesn't fully account for the effects that we see. So we started looking at the patterns of various different emission lines. So not only at the O3 to H beta versus nitrogen 2 to H alpha ratios, but extending our search of these different emission lines to different spaces. So we looked at O3 to H beta and sulfur 2 to H alpha. We looked at O3 to O2 and that R23 indicator. And what was the thing that was interesting, and then we can also look at, if we dust correct this, dust-corrected lines, which we need to do here. What we see is that the redshift 2 galaxies, which are indicated by green points in this plot, and the gray histogram is the local galaxies, is that there's no analogous offset in these other diagrams, like there was in the first diagram I showed you, the O3 to H beta versus N2 to H alpha, okay? So an offset is observed in these line diagrams that involve nitrogen, which is consistent with an elevated nitrogen 2 flux. And so our interpretation, until fairly recently, though I'd say it's a little bit in flux now, is that these redshift 2 galaxies typically have high ratios of nitrogen to oxygen at fixed oxygen abundance compared to redshift 0 galaxies. Okay? So if you want to estimate the oxygen abundance, it seems like sort of obvious in retrospect, you should use metallicity calibrations of strong lines that don't involve nitrogen and just use lines that are based on oxygen, okay? And that's what's shown here is basically, this is a calibrations from some local galaxies where you can see there's a nice smooth progression going from lower metallicity to higher, going from higher metallicity to lower metallicity in this space of O32 versus R23. And this is where we're gonna concentrate a lot of our effort because we think that the totality of our MOSDEF data so far suggests that the ratio of this interstellar nitrogen to oxygen may be different at redshift 2, and that we need to avoid oxygen indicators that are based on nitrogen lines, which unfortunately, I'd say it's been very common to use nitrogen lines to estimate oxygen abundances in the early universe because it's convenient. You're looking at two very closely spaced lines. You don't have to worry about how dust affects one line relative to the other because they're so close in wavelength. You don't have to worry about your flux calibration that much. But it actually seems like for now, we should avoid these oxygen abundance indicators based on nitrogen and use only indicators based on oxygen and hydrogen, which we've actually been collecting. So that seems to be the way forward. And one thing that was super heartening, and I'm basically done, I just want to show you a couple of other things really quickly, was everything that I've shown you so far at redshift 2 has been based on just these patterns of strong emission lines. In the local universe, there are these attempts to calibrate the strong emission lines to directly measured oxygen abundances. And it's very hard to do that at high redshift. But it turns out it's not impossible. So one of the things that was super exciting in the MOSDEF project is that we actually, just barely, at a level of 4 sigma, we actually detected that weak 4363 oxygen line here. Okay, and you can see here it is in a plot of signal to noise versus wavelength. Here's that weak line. Here it is in 2 dimensions. There it is. And there's a neighboring line from hydrogen. Okay, and so we actually made a direct oxygen abundance measurement at redshift 3.08. Okay, which suggests that redshift 3 galaxies, at least based on this one galaxy, follow roughly the same relationship between the strong lines that are easy for us to measure and the directly measured oxygen abundance, which is very difficult to do. Okay, but this is an active area of research, and we're hoping to really figure out more what's going on. Okay, so I want to just close with a couple thoughts about spatial resolution. So remember I showed you these plots of the Sloan Digital Sky Survey and MOSDEF and what it means when you get a spectrum of a whole galaxy. And so the question is, what do we miss when we get one spectrum of a galaxy and we don't have any spatial resolution, okay, as opposed to this image from the chaos survey where they're putting individual slits on all these, or they're putting slits on all these individual star-forming regions and really getting a detailed view of the individual subregions of the galaxy. So if we get a single spectrum, so one of the things we're missing is an accounting of the relative contributions of diffuse ionized gas and these high surface brightness regions of star formation. We're missing a detailed accounting of the contribution of active galactic nuclei. We're missing if there are any kind of radial dependent gradients of the properties in the galaxies. We're missing any difference in the properties of sort of like high surface brightness regions, what we call clumps. And so we're actually in the middle of trying to address these shortcomings by using an instrument called OSIRIS on Keck to get much better resolution than what we have. So rather than several kiloparsecs, we're moving to a resolution of 1 kiloparsec. And we've tried to start doing this. We haven't had such good luck with the weather so far. But what we're going to do is we're going to use OSIRIS. This is what we call an integral field unit spectrograph fed by adaptive optics. It gives us better spatial resolution. And we're going to try to map the line ratios and the motions in the galaxies, across their faces to get a much more detailed view of what's happening in the interstellar medium of these distant galaxies, okay? And so I want to just put up my conclusions, and I want to just show you something really fun that's not related to what I've been talking about, but it's something else that's exciting that's coming out of our project and related observations. So hopefully what I've shown you is that if you get simultaneous coverage of multiple rest frame optical emission lines at redshift 2, you can untangle many physical processes in galaxies. One of the things that we're very worried about at UCLA is trying to estimate oxygen abundances in galaxies over cosmic time, because we think it's going to be very useful for constraining models of galaxy formation. What we've seen with MOSDEF, and there are other projects too looking at this, is that there may be different abundance patterns in these early galaxies. Understanding why is very important, or it may be some other processes, okay, because this is actually sort of a controversial point here. But we want to understand why exactly these high redshift galaxies look different. But for now, for those of us trying to estimate oxygen, I think we have a good idea of how to proceed just using the oxygen and hydrogen lines. And I just want to say, this is actually really important. There's going to be a lot of near-infrared spectroscopic data coming to us over the next decade. Okay, there are projects like the James Webb Space Telescope and the WFIRST satellite. Okay, we're going to be getting lots of near-infrared spectra, and I think it's very important for us to try to understand how to interpret all these spectra in a meaningful way. And that's one of the reasons why we're trying to look at the spatially resolved properties of the interstellar media in these high redshift galaxies. Okay, so let me just put up something really fun. That's the last thing I'm going to do. I'm not even going to talk about it. But one of the things that MOSFIRE has enabled that was just basically impossible before MOSFIRE was the ability to do absorption line spectroscopy at high redshift. Okay, so here we have enough signal that we actually can look at the continuum. Okay, these are nanometers here, and look at stellar absorption lines. And this is something that our collaborator Mariska Creek did in a recent Nature paper, taking one of probably the most luminous galaxy in our survey, and actually looking at the pattern of stellar absorption lines from different chemical elements, and using this to look at the star formation history of this really massive, sort of already basically dead galaxy at a redshift of 2.09, so it's about 10 billion years ago. And you can actually look at the abundance pattern from different chemical elements, and it tells you stuff about how this galaxy was put together. And there's going to be a lot more of this coming out from MOSFIRE and also from future facilities, so stay tuned. Thanks.
Thanks, Alice. Any more questions?
I was wondering, so you talked a little bit about the excitation mechanisms that might drive the outflow of AGN or at least in the local universe, I think shock seems to be a very playing an increasingly prominent role in driving these outflows. Is that the case in high redshifts and UCZ2 galaxies as well?
Bill, okay, so the question is, how important are shocks in driving outflows? So it's something that we're investigating. I think Bill is looking at this right now. I don't know, Bill, maybe you want to say something about it. Should I give you the mic so it goes on the record? Here. Oh, just, okay.
The shocks aren't necessarily driving the outflows, but we're definitely seeing them as a result of the outflows.
But are they very prominent in terms of their contribution to the... but you see them.
That's what I think
Yeah, in principle, you can try to identify the importance of shocks looking at the line ratios as well. So something that we're looking at.
I have a question.
Yeah, sure.
So the one galaxy at redshift of 3.09 that you could use.
Oh, yeah.
physics.
Yes,
So
physics.
that's the one where you use physics to determine the oxygen abundance. What does the nitrogen abundance look like for this?
Oh, well, what am I going to say? Yeah, so if you may recall, let's go back a little bit. That's a great question. I wish I had the answer, but you'll see why I don't in a second. Hang on. Okay, so remember I said that we use windows of atmospheric transmission to study the galaxy. So you can see that if this galaxy were at redshift 2, we could study the nitrogen 2 line in the K-band, okay? But it's at redshift 3, so this actually moves into what we call the thermal infrared. So we'll just have to wait for the James Webb Space Telescope. We're definitely going to put it on, our first set of observations, if we get time, we'll study this galaxy.
Yeah,
So
unfortunately, it's not one of your redshift 2 galaxies that you were able
it's not, no. But there are many reasons why it'll be great to observe this at longer wavelengths, because another thing, if you want to look at the ratio of lines at different rest frame wavelengths, you actually need to correct for dust extinction. And so the robust way of doing that is looking at the ratio of this line, and we don't have this line either for this galaxy. So it's going to be much better when we get data over here at beyond 3 microns. And the instrument that's also called NIRSPEC, like the Keck instrument, but it's on the James Webb Space Telescope, will give us continuous coverage from 1 to 5 microns. And so we'll be able to do this.
You won't suffer from the windows.
Yeah, so anyway, so it's a great question, and we'll hopefully be able to answer it in just a few years.
So how did you measure this 25 to 150 number this telcast?
How did, sorry, can you say that?
Measure the number this telcast, you mentioned 25 to 150.
Oh, with the doublets? Okay, so the question was, how do we estimate the density of the gas? Okay, so, let's go, sorry, okay. Right, so it turns out that the ratio of these doublets is sensitive to the density of the gas in the H2 region. So basically, it's sensitive to whether it's sensitive to basically the presence of the collisional de-excitation in the gas. And so if you're in a low density regime, the line ratio is going to asymptote to one extreme, and if you go to higher density, you'll asymptote to a different regime. And so there's a very nice sort of simple relationship between the level populations for these two doublet members and the density. So yeah, so it's a wonderful sort of like one-to-one density indicator. But again, I should say that when we look at these in the galaxies, we're looking at the average density over the ensemble of H2 regions. It's not quite as good as looking at the density in one star forming